Thank you, everybody, for taking the time to join us this evening. I serve the Midlands branch of Engineers Ireland. I'm delighted to welcome Vortech to give us a presentation on harnessing the power of vortex flows. And I would like to thank the Water and Environmental Society for their support in hosting this presentation. So the presentation is going to be delivered by Fergus Clifford of Vortech, and it is going to focus on providing an introduction to the fundamental principles of vortex flows. It will outline how vortex flows can be leveraged in the field of hydraulic structures and wastewater treatment. The presentation will include case studies detailing real-world applications of the deployment of vortex flow-based infrastructure and technology to solve complex engineering challenges on infrastructure projects globally. The presentation will then provide insights on how computational fluid dynamics can be utilized at the design stage of hydraulic infrastructure projects to provide valuable design insights and identify key risks prior to construction. Fergus, who will be presenting, is the head of operations at Vortech Water Solutions, a Galway-based wastewater technology company providing engineering solutions to the wastewater treatment industry. Fergus is a chartered engineer with Engineers Ireland and is a licensed professional engineer in Ontario, Canada. Fergus has over 15 years of international experience in the field of civil and environmental engineering, encompassing project management, design, construction, and contract management. His areas of expertise include water and wastewater treatment, infrastructure, stormwater and sewage conveyance, drinking water distribution systems, hydraulic structures, trenchless construction, and hydrology. Now, Fergus holds a Bachelor of Engineering, Environmental Engineering from the University of Galway. So now I'd like to hand over to Fergus to begin.
Thanks very much, Alan, for the introduction, and thanks, Maury and John, Engineers Ireland, for facilitating tonight's webinar. And lastly, I guess thanks to everybody for jumping on after a hard day's work. So before I get into the technicalities of today's webinar, I want to kind of plant a seed with everyone. And I suppose just to think about how nature is all around us, but nature also challenges us, particularly when we think about water, wastewater treatment infrastructure. So climate change, climate weather events, they actually put stresses on our infrastructure. But in the same breath, nature has actually provided a lot of solutions to challenges that we face day to day. So like a good example I like to think of is the area of aviation. Humans saw that was possible through nature, and were able to design machines and aircraft that were able to fly. So I think that's a central theme of today's webinar, is how we can learn from nature and harness natural phenomenon to solve real world challenges in engineering. So a little bit of a background on myself. I'm not going to go into myself because Alan's already given a fairly comprehensive introduction, but just to give a little bit of background on Vortech Water Solutions, who we are and what we do. We're a Galway-based wastewater technology company. We've developed a proprietary wastewater aeration technology, which is inspired by fluid dynamics and the core principles of vortex flows, which we're deploying in treatment plants in Ireland, UK, Australia, and further afield. Our team is made up of a multidisciplinary team of both engineers and scientists, but I mean, our team is kind of cut from the same cloth in the sense that we're all fairly technically astute, but at the same time, we're not afraid to roll up our sleeves. And we've all been on site. I mean, I've been on site inspecting pumps at some of our wastewater installations. A few of my colleagues have not just inspected pumps, but actually maintained them, lift them out. So we're not afraid to get hands-on. And I think that's one of the reasons why we have unique insights in the area of hydraulics and fluid dynamics. As a purpose for the company, it's pretty clear. What we're trying to do is encourage communities, industries, various stakeholders to embrace safer, better, environmentally friendlier, more energy efficient water management practices. So really, there's three things that I want to try and convey from today's presentation. And the first thing is to cover fundamentals of vortex flows. So what is a vortex flow and how is it described in scientific or engineering terms? And then look at practical applications for this natural phenomenon in hydraulic structures and in the field of wastewater treatment. So just to set the scene, the global context, particularly when it comes to urban infrastructure and conveyance systems, our cities are facing significant challenges today. So an obvious one is rising populations, but also water consumption per capita and generation of wastewater per capita is increasing in many different areas as well, putting strain on existing infrastructure. Rapid urban development is putting strains on our infrastructure. So I had a couple of colleagues in Abu Dhabi last week at a conference, and an interesting fact I heard was the municipal area in Abu Dhabi has grown in size by 1,700% over the last 40 years. Incredible expansion, rapid expansion. But with that comes severe strains and challenges on the water infrastructure in that region. Climate change is an obvious one. This 100-year storm 20 years ago is more frequent today. But coupled with that, and ironically enough, even in Ireland, water availability and scarcity is becoming a significant challenge globally. And while we're probably less prone to that in Ireland, even the Shannon pipeline to Dublin to shore up our capital's future water resources is an example of how even water availability actually does impact a country like ours. So let's consider a typical urban area. So we've got our city and we've got our existing infrastructure. And when we consider the challenges on the previous slide, many cities around the world, the existing collection infrastructure, which is just a system of storm and sanitary sewage systems, or combined systems, is coming under stress. And if we want to avoid adverse impacts to the environment, like discharges to natural water bodies or even flooding impacts to our economy, we need some sort of a way to intercept the flows which are exceeding the hydraulic capacity of our infrastructure in these cities. And the main way that that's been done to date is by going down. So we sink drop shafts into the ground and we construct deep tunnel conveyance systems, which are designed to intercept these flows, to store them, and also to eventually convey them to some kind of wastewater treatment infrastructure where it can be treated, potentially even reused, and discharged back to the natural environment. So in today's webinar, we're going to focus on two particular areas of this overall infrastructure thread. And that's the deep tunnel segments, so the drop shafts and the deep tunnel conveyance system, and also the wastewater treatment infrastructure. So what we're looking at here is a typical vortex flow formation. And at first glance, it might seem quite chaotic. But in reality, it's actually a very predictable and controlled process. So if we dropped a little particle into this vortex flow, we could actually predict over time what velocity it would travel at, what its trajectory would be, what the pressure drop would be from A to Z. So with that in mind, what it means is there's a natural phenomenon which is predictable and potentially could be leveraged to actually solve some of the challenges that we've discussed on the previous slide. And one of the ways of doing this is the use of vortex drop structures, which I'll come on to in a minute. But just to cover the fundamentals of vortex flows. So I mean, what is a vortex flow? In layperson's terms, it's simply just a fluid flow mass revolving around an axis. So we've all seen it in some shape or form, whether it's a hurricane or a cyclone. We've seen it in, pictures of galaxies, space. Even when you stir a cup of tea, you generate a vortex. So we've all seen it in some shape or form or capacity. It's a naturally occurring phenomenon. And really, from a scientific perspective and an engineering perspective, the three main characteristics of particle motion in a vortex flow are described by its tangential velocity, its angular velocity, and its kinetic energy. So if you look at the schematic below, if there's a few hydraulic engineers on the session this evening, you'll probably recognize some of the formulas. There's velocity head down on the bottom left and the bottom right. There's also a formula there for literally angular velocity. But the formula there on the top right is an interesting one. It describes the tangential velocity of a particle in a vortex flow. And that constant on top of the equation, lambda, is fixed. So immediately we can see that there's a relationship between the velocity of a particle in a vortex flow and the radius from the central axis of the vortex flow. So when the radius gets smaller, the particle speeds up. And that's a key characteristic of vortex flows, which can be leveraged in big engineering projects globally and even in the wastewater sector as well. So coming back to our city, we've got our existing infrastructure, we've got our infrastructure that's under pressure. We need to send the excess hydraulic load somewhere. So I guess the first part of the webinar is going to focus on the deep tunnel conveyance system. And in the second part of the talk, we'll do a deeper focus on the wastewater treatment side. So I'd mentioned vortex drop structures. Many of you in the webinar will already be familiar with these types of hydraulic structures. They're really used all around the world. So I've given an example of a few mega projects across the world where deep tunnel sewers have been constructed and vortex drop structures have been integrated as part of that overall tunnel system. One project in particular that we'll focus on in a few slides, a little bit of a case study, is the London Thames Tideway. Before I joined Vortech, founder and CEO Sean and a couple of the original staff had actually worked on that project in collaboration with Ward and Burke to help validate an innovative solution to a challenge along a segment of the Thames Tideway Tunnel. So we'll focus on that in a few slides, but a couple of other projects just to run through, like in the Middle East, Dubai, Doha, Abu Dhabi. You might think because they don't get much rainfall, why do they need this kind of infrastructure? Well, we talked about it, like the rapid expansion in urban growth in these areas, and also climate change. So the existing infrastructure that was constructed when these cities were expanding the hydraulic capacity isn't sufficient for some of the storms that they're seeing, even though they're seeing them rarely. Cities like these can actually still experience flooding. The Hong Kong deep tunnel is another interesting one. I heard a statistic recently where I think it's upwards of 210 cubic meters per second in peak flows flowing through that system. Incredible flows. And the Toronto deep tunnel was actually a project that I worked with in Toronto when I worked in Canada for about 8 years. On the east side of Toronto, the Don River runs along the city. And again, it's the same challenge that a lot of older cities, let's say, I mean, Toronto isn't an older city, but a lot of the sewage infrastructure there is quite old. Hydraulic capacity insufficient, and during wet weather events, particularly some of the combined sewer segments will literally overflow into the Don River, which makes its way into Lake Ontario. So there's significant environmental and pollution concerns associated with that. And that's why these projects are necessary. One thing to bear in mind though, when you're dropping flows to such depths, so we're starting off at a high elevation and we're dropping flows 20, 30, 40, even 50 meters. The mass of that fluid column is substantial and the forces that it can generate are massive. So an interesting stat I came across recently was your typical drop structure vortex drop structure can dissipate up to the equivalent of 6 tons of TNT per hour in force, so incredible forces generated. And we need a way to drop those flows safely so that they're not damaging our infrastructure or causing erosion, let's say. So how do drop structures work? Again, most of you will be familiar with this, but we've got a linear flow coming in from a conveyance system, which is a sewer. So if we track our little particle coming in, it's got a linear velocity, linear momentum. And this vortex generator, which is just a specific geometry designed to induce a vortex when an incoming flow meets it at a particular trajectory. This vortex generator converts the linear momentum into angular momentum. So now our particle, it's got linear velocity. Now it's flowing around the vortex generator with an angular velocity. But as it's moving in towards the middle, towards the vortex core, it's speeding up. So we talked about that in the previous slide. When the radius is decreasing, our velocity is increasing. And when it enters the drop pipe, because of its velocity, it's got a significant centripetal force, so it grips the walls. And over drops of 20 or 30 meters, you can dissipate a substantial amount of energy because of the centripetal effects and the friction effects. So that's how we're able to do this. And on the right-hand side, you can see kind of an overall schematic of your typical vortex drop shaft and how that connects to your deep sewer segment. So just an interesting kind of map of deep sewer projects that have been rolled out across the globe. You can see a lot of cities in North America are now pursuing deep tunnel projects because of flooding issues that they're having and insufficient capacity with their existing infrastructure. Thames Tideway is a massive project. The Toronto Deep Tunnel I worked on briefly, but you can see that like large urban areas are now having to start constructing these vortex drop shafts and deep tunnel segments to deal with capacity issues. So just as an example, and this example is intended to show how it is the CFD angle. So how can we leverage the numerical world or the simulation world to predict how flows are going to behave through different types of drop infrastructure, hydraulic infrastructure. So this particular project is a vortex drop shaft that Vortech simulated for a client in Wellington in New Zealand. And you can see in the simulation domain on the left-hand side, compared to the actual result on the right-hand side, that it can provide you prior to construction with a very good insight on how the fluid is going to behave under different flow conditions. So you might want to examine how it's going to behave under peak wet weather flow, or you might want to examine how it's going to behave under dry weather flow conditions to get the full variation. So this is where CFD can be leveraged as a tool to understand the behavior of these structures prior to construction and also identify particular risks. So maybe our vortex insert it doesn't have enough depth and it overflows during certain peak flow conditions. So it allows us to spot risk in advance and make design tweaks prior to construction. Another case study I want to run through quickly is the London Thames project, which I alluded to earlier. You can see that this is a fairly extensive deep tunnel project, which is constructed in London over the last decade or so. There are various different parts to this project. The element that we were involved in was a section around the Putney Bridge, again, prior to my time. But to provide a little bit of context on the challenge here, on the left-hand side, you can see the existing type of sewage infrastructure in London. And like London's sewer system has been constructed from the 1800s onwards. So it's an incredible piece of engineering, but it was also built for the demands of that time. And the demands of our time are substantially more. And you can see the results of insufficient capacity in these systems on the right-hand side. So combined sewer system, wet weather event, storm flows combined with sewage, overflow events occur, and inevitably the combined sewage just makes its way into the River Thames. So there's an environmental impact and there's a water quality impact. So that's the purpose of the Thames Tideway project. The particular segment that Ward and Burke were involved in and that we collaborated with Ward and Burke on was around the Putney Bridge. So it's a heritage monument in England. It's an important piece of architecture in London. And directly underneath the bridge, there was a combined sewer outfall, which essentially just served as a discharge point for sewer overflow from the existing sewer system. So Thames Water wanted to capture the combined sewer overflow from this CSO and convey it to the new deep tunnel system where it could be stored and treated in the future rather than being discharged into the Thames. And the original concept was to construct kind of an enclosure around the an interception enclosure, around the CSO, and then open cut, excavate just a gravity line to flow control configuration with penstocks and valves, and then drop it down in a drop structure to the deep tunnel system. But this concept presented significant challenges, particularly with the open cut element in such close proximity to the abutments of the bridge. It presented structural concerns and structural risks. So Ward and Burke came up with a very innovative concept, and I've worked with them in Canada as well on the trenchless front. Very good contractor, very good when it comes to microtunneling as well. But they come up with a very innovative trenchless approach for intercepting this CSO. However, this approach required validation with Thames Water. So there was an existing design which had been validated, and Thames Water wanted assurances that this new concept would work. But what this concept would deliver is a substantial reduction in the overall cost, significant reduction in time on site, which means less disruption in the city, protection of a natural heritage monument, and also because of the vast majority of what was being proposed was trenchless, it eliminated significant kind of above ground disruption to do with open cut excavation. So really you would have only had localized excavation where the reception and launch shafts would have been. So the role that Vortech played in this project was to help Ward and Burke with the numerical and physical validation of this new concept. And how we did that was we actually constructed a scale model of this sewer segment in NUIG in Galway. And that scale model is actually still in the hydraulics laboratory today. And what we were able to do was simulate physically. We were actually able to physically test different flow configurations through the scale model. For example, we were able to look at the tidal influences on the Thames on conveyance. We were able to look at the impact of grit, gravel, debris getting into the system and how that might be evacuated. So there's lots of different things that we were able to demonstrate to Thames Water by constructing this physical model. Here's a video of the segment between the TSO and the actual drop shaft. So the key element of design here is the ability to expel air from the system, because what we don't want is an airlock forming, which will impede flow to the conveyance system. So that was a key aspect of investigation for the physical model. And here are just a couple of clips still showing the actual discharge point. So this is the drop point into the actual deep tunnel sewer. And again, the principles of vortex flows are leveraged here, because what we want to do is be able to dissipate a lot of the energy from that incoming flow before it hits the next level, being the interceptor sewer, which is tens of meters below this segment. So coming back to our city again, we've talked about how we can potentially deal with challenges for the existing collection infrastructure in our urban area. And now that we've captured those flows, they inevitably make their way to some kind of a pumping station from where they're conveyed to a wastewater treatment facility. And this presents another challenge. So again, going back to the context, specifically when we look at wastewater treatment, population increases, more water consumption. That means more volumes of wastewater are being generated in our urban areas, and that's a rule of thumb, broadly speaking, globally, including in Ireland. One key element that's now come on the radar in recent times is the energy intensity of wastewater infrastructure. I read a statistic recently. I think approximately 3 to 4% of global energy consumption is associated with wastewater treatment. So it's very significant. In addition to that, you've got carbon emissions associated with the energy use, but you also have things like nitrous oxide emissions from wastewater treatment plants and methane emissions from wastewater treatment plants, which also have a significant carbon footprint. There's also more pressure being put on existing infrastructure from the regulatory side. So we've got more stringent wastewater treatment requirements, and in many countries around the world, Australia is a good example of this, treatment plants now need to be able to actually treat wastewater to a point where it can be reused. Some cases even for drinking water, but in many cases at minimum for things like irrigation. All of this in the context of aging infrastructure. And again, just focusing on Ireland, much of our wastewater infrastructure is decades old, treatment infrastructure. With Uisce Éireann, in fairness, there's a lot of new water and wastewater treatment plants being constructed around the country where demands are required. But a lot of our treatment plants are very old. And because we have aging assets and aging infrastructure, it's kind of putting a demand on our existing treatment plants to do more with a lot less. So little bit of a kind of a basics on your typical wastewater configuration. So in the vast majority of wastewater treatment plants around the world, you'll have primary treatment and secondary treatment. And in some cases, you'll have tertiary treatment as well. And primary treatment, in a nutshell, I like to describe it as kind of crude treatment. So that's your removal of debris, removal of grit, and removal of settleable solids. Your secondary treatment is really where that's kind of the workhorse of a wastewater treatment plant. That's where all of your soluble contaminants make their way. And this is where the vast majority of energy consumption occurs, and it's specifically in the aeration tank. So aeration can consume upwards of 3/4 of wastewater treatment plant's energy bill. That can vary between 50, 3/4, but it's a substantial energy footprint relative to the overall treatment plant. And what that means is if you're going to try and make a significant impact on the energy consumption, carbon footprint of wastewater treatment infrastructure, this is the area that you're going to focus on first. So just to do a little bit of background on wastewater aeration, what is it and why is it necessary? Well, wastewater aeration in simple terms is simply the introduction of dissolved air and dissolved oxygen into wastewater fluid. And that's done by many different mechanisms, and we'll talk about that in subsequent slides. But really, the reason it's necessary is because you can see here, the secondary aeration process is referred to normally as the activated sludge treatment process, which basically involves the mixing of wastewater with suspended bugs, I'll call them, suspended bacteria. And these bacteria require oxygen in order to remove the oxidizable contaminants, soluble contaminants within the wastewater. They need oxygen simply just to sustain themselves, just to survive. And they also need oxygen to remove nutrient contaminants from the wastewater, primarily in the form of nitrogen-based nutrients like ammonia, for example. So that's why aeration is necessary, and it's really the workhorse and the most crucial part of wastewater treatment beyond the physical treatment. Little bit of a background on wastewater aeration technology. So the activated sludge process was invented probably like over 100 years ago, towards the end of the 1800s or the beginning of the 1900s. And from then up until maybe the 60s, maybe beyond the 60s, the go-to way of aerating wastewater was simply by surface agitation. So rotating mechanical aeration devices. And what they do is they agitate the surface. That induces a kind of an air-water mixture, and you get aeration from that. So beyond the 1960s, a lot of work started to be invested in looking into alternative, more efficient methods of aerating wastewater. And what's kind of commonly referred to as the best-in-class technology today is FBDA, or fine bubble diffused aeration. And it's the most efficient way of aerating wastewater. However, both of these technologies pose significant challenges. And really, since the inception or the invention of wastewater aeration technology, many of these challenges have not yet been solved. And in particular, with FBDA, fine bubble diffused aeration, that's been the predominant form of aeration over the last number of decades. But a lot of the simple issues just haven't been addressed yet. So, for example, these technologies can be quite difficult and very costly to install. In many cases, they're energy inefficient. So, as an example, with fine bubble diffused aeration, you can get deterioration in performance over time because the nature of the wastewater constituents can actually coat the little diffusers that inject oxygen bubbles into the reactor. Maintenance costs is something that's been overlooked to a very high degree up until recent times. For example, with typical mechanical aeration, it's got a lot of moving parts, a lot of wear and tear. For example, motors, gearboxes, rotors, bearings, all of which need to be replaced because these things are oftentimes operating 24/7. Fine bubble diffused aeration, it's installed at the bottom of a tank. So if you want to maintain it, you need to drain the tank, which is very costly. And if your plant doesn't have redundancy, it leaves you with minimal options for how to actually do that. In some cases, we've heard instances of scuba divers being sent in to repair FBDA grids. So sometimes it can be disastrous. That leads into unsafe work environments. And in many cases, the longevity of these technologies is very short. So, we've seen instances of wastewater treatment plants where the FBDA grids don't last longer than 5 years and need to be replaced. So really, what we're trying to do is understand how can we take the benefits of both of these existing legacy aeration technologies and blend the best parts of both while also eliminating the challenges associated with both. So we talked about how mechanical aeration, one of the benefits is it's surface mounted, so it's easy to access from a maintenance standpoint. It's relatively efficient, but in many cases not as efficient as other options. But what it does poorly is generate fine bubbles, which is necessary for oxygen transfer. Then we've got fine bubble diffused aeration, which is very good and efficient at generating fine bubbles, but which is installed at the bottom of a reactor. And that makes maintenance extremely challenging. External blowers pumping air into tanks, and sometimes diffuser heads can pop off. So what we've done at Vortech is taken the best of both worlds. We brought aeration back to the top of the tank, but we're utilizing the fundamentals of vortex flows, which I talked about earlier, to generate fine bubbles and inject those back into a wastewater reactor efficiently. So just to show you a little bit about our technology and how it works, there's really 3 to 4 parts to the technology, and there's only one moving part, which is a column pump or an axial flow pump. And how it works is there's an inlet column which is submerged within the reactor, and the pump draws activated sludge from the reactor, circulates it through the vortex device. An orifice on top of the device is open to the atmosphere. So if you can imagine, we're stirring the cup of tea, and in the middle there's a zone where air is constantly getting drawn in. So that's the same as what happens in principle. Air is drawn in. We've got well understood conditions, but high turbulence conditions existing within the vortex chamber. And at our air-water interface, when it's being discharged back into the reactor, that's where we get a significant amount of oxygen transfer. And we can inject that oxygen into the wastewater efficiently. You can see on the right-hand side as well that not only does our device entrain oxygen, but it also mixes the reactor. So there's a secondary benefit because mixing is a key element of the activated sludge process. You need an equal concentration or density of bugs in every part of the reactor and an equal concentration of dissolved oxygen in every part of the reactor for the process to be effective. So this video just shows you how the innards of the technology actually works. And the video's jumping a little bit here, but you can see the stable, but kind of, it appears chaotic, but quite stable vortex, which is generated within our device. And then the orifice at the bottom is where the air and liquid combined discharges back into the reactor, and you get air entrainment occurring. So it's a very simple device, and it's simply reliant on circulating the fluid within a specifically designed geometric structure to induce a stable vortex. So a couple of case studies we'll look at. The first one is an abattoir facility, which we installed one of our devices at in Somerset in the UK. And just to talk through some of the challenges that the owner of this facility faced. So the facility production load, they needed to increase production capacity within the facility by 30%. That was the expected increase in throughput in terms of cattle. And as a result, they needed a wastewater treatment plant which was designed to treat the population equivalent of about 19,000 people, so bigger than a small town. And that was to treat the wastewater generated from that livestock process. Their existing treatment stream was quite crude, so really all it involved was solids removal using what's called a dissolved air flotation device. And then the effluent from that was just simply discharged to the municipal sewer. And for every cubic meter that they discharged, the owner of this facility was being charged significant trade effluent charges. So you can see it was upwards of about tons per annum. In addition to that, significant chemical usage was required as part of the DAF. So what they wanted was something that could be fit quick and efficiently increase their capacity, was fit and forget, more or less low maintenance, low energy consumption, and also because there was existing dwellings nearby, they needed to make sure that there was minimal noise generation from whatever aeration device was used. So we proposed a 63 kilowatt variation of our Vortex powered aeration technology. We were able to deliver the technology on site in a modular fashion. We have a design philosophy called design for manufacture and assembly, which means we essentially try and make everything as flat pack as possible and as easy and rapid to install on site. So you can see between the mechanical assembly and the electrical install, it took 10 days in total. And we also provided a control unit actually for the machine. So we were able to, using basic instrumentation like dissolved oxygen instrumentation, we were able to provide a pre-programmed PLC which could effectively control our aeration device automatically without the need for intervention from the operator on site. And that resulted in significant energy and associated carbon emission savings. So the results of the install speak for themselves. We were able to dramatically improve the treatment outcomes on site in terms of removal of biochemical oxygen demand and also ammonium. We were able to deliver on the increase in the site production capacity, all while lowering the specific energy consumption. So what I mean when I say specific energy consumption is the kilowatt hours expended per kilogram of BOD removed from the wastewater. So relative to another site that this owner was operating in the UK, we reduced their aeration energy consumption by 30% relative to that other site. And then really the benefit is gained in the long term. So it's the total life cycle savings over 20 years to the tune of 2 million euros. And we were also able to eliminate their chemical usage or dramatically reduce their chemical usage. We also eliminated the trade effluent charges. So not only were substantial costs eliminated, which they incurred previously, but also they got benefits in terms of reduced energy consumption and fit and forget, reduced maintenance requirements. Another case study, which I'll run through quickly, is actually a municipal site here in Ireland. It's a small wastewater treatment plant in Mayo, population equivalent of 3,300. And the existing wastewater treatment stream, it was divvied up into 2 aeration streams with fine bubble diffused grids. So we observed a load increase at the facility in 2021, and we were noticing significant variations seasonally as well, which could be attributed to, agricultural activities. It could be attributed to lots of different things. What we were able to do at this facility prior to the Vortex powered aeration install was actually baseline the energy consumption of the existing aeration approach on site, which is blowers combined with fine bubble diffused aeration. So that served as a benchmark for comparison for the retrofit of our technology. And what we did at this site was we put in a single 22 kilowatt Vortex powered aeration device. As I showed earlier on the computational fluid dynamics model, because we are able to simultaneously aerate and mix, this meant that the submersible mixer, which was necessary for mixing for the fine bubble diffused aeration install, was now redundant. So we were mixing and aerating at the same time. Again, simple benefits in terms of rapidness of installation and getting it operational. Mechanical installation was only 3 days. And we also supplied, again, a control unit for the VPA unit, which included the actual PLC and instrumentation, which could automate the control of the aeration device on site and ensure that it was operating at its most efficient point, depending on the loads coming into the treatment facility. So I suppose that this is kind of where I wrap up, but the question that we asked ourselves at the start of the webinar was, has nature provided us with a solution to some of the challenges that we're dealing with in various aspects of engineering? And from our perspective, it actually has, in the form of vortex flows. We've been able to leverage this natural phenomenon to deal with challenges in the conveyance side and in the wastewater treatment side. And with that, I'll wrap up. But thank you, everybody, for joining today's presentation. And I think we're going to jump on to some Q&A.
Fergus, perhaps I'll start just with thanking you for a fascinating presentation. My first job out of college was in wastewater treatment, and I can just imagine that for this repair of the fine bubble diffuser using the scuba gear, the queue was queue of volunteers would have been significant. But I suppose also I went to an open day at a local secondary school there a while back, and in the science lab they had bottles of water, and they're asking the children to empty the water as quick as they could, and children were shaking it and hitting it. But when they introduced a vortex or a swirl to the liquid, that was how it was emptied the quickest.
Yeah.
So to see it taken from that, a simple concept in a school to a global, and I suppose the complex application of it, while it's still being the same thing effectively, is fascinating. I was just wondering on the physical model for the London project, and just I imagine there was lots of fun rerunning models and changing the parameters. But I was just wondering what were the main findings, or kind of what did that show? Did it show, was there any particular issue that it kind of highlighted from the kind of physical, and how it kind of linked the physical and the computer modeling of the project before it went to construction?
It's an interesting question, and like I'll throw my hands up now, Alan, and say like I wasn't around Vortech when they actually did it, but I do know a bit about it, and I have seen the model in the university as well. But I think the key element, like for me, there's two key elements to doing that. Number one is Thames Water. Obviously, they had an engineering consultant who had already designed a concept which worked, So that was number one. And in fairness to Warden Burkett, like I've worked with them, not just in Ireland, but in Canada as well on different projects. They're a very innovative contractor. And they came to the table with kind of a value engineering approach. And they felt that there was a better way of doing it. But obviously, Thames Water required a bit of convincing. But in addition to that, I think from a design perspective, because this was Warden Burke's design proposal, it was beneficial to them because it allowed them to physically model certain scenarios which could actually impact conveyance in their new proposal. So like for example, we talked about the impacts of the tidal impacts on the Thames River and how that might influence the head in certain areas of the system. The other areas, like what if debris gets into the system? Is the system designed in such a way that it can easily expel a plank or a piece of timber or a trolley or something like that? Because we all know that stuff like that does get into sewers. Another key one was the airlock as well. That was really interesting because and again, I'm kind of explaining this in layperson's terms, but the slope of the sewer made it a difficult challenge to actually expel air, which is key because like when you've got flow coming in, it's displacing air, and the air has to go somewhere. Otherwise, if you don't have a good place to displace the air, that's where manhole lids get popped off in cities like New York, and even in Toronto, I've seen it before. So basically, it allowed them to examine these different scenarios and provide a bit of surety and certainty with the design prior to mobilizing on site. And even the CFD, it was useful prior to actually constructing the physical model because you can check different scenarios in the numerical world first, and then you can get a reasonably good indication. Okay, we think this physical model might work. We think this design might work. So now you're on the right track when you expend a good bit of capital to actually build a physical model like that.
Yeah. No, that's fascinating, and I suppose it's great that it's still there, that it
It
can be
is.
used as a learning aid and going
It
forward.
still
So
works actually. Yeah. Yeah, it does. Yeah.
excellent. We have a few more questions, Fergus, if that's okay. So Adam has
Yeah.
asked, how is the efficiency of oxygen transfer as compared to the fine fine bubble diffused aeration system?
That's an interesting question, and that's probably a presentation in and of itself. But I'll try and give you a quick answer on that. So there's like if you look up on if you just Google aeration efficiency of fine bubble diffuse systems online, you'll find values in academia ranging between standard aeration efficiencies as low as like lower than as low as two to upwards of five, six. Some vendors will claim that they can achieve SAEs of six, and I don't believe that. But anyway, that's a separate thing. Our aeration device, we have tested it in a clean water setting, and it has a minimum SAE of 2.5, which is more efficient than most surface aeration technologies, less efficient than fine bubble diffused aeration. However, there's a key point that needs to be considered, and that's how efficient is it in process water as opposed to clean water. So whenever you see somebody telling you the standard aeration efficiency of their device, that's in clean water. So they've tested the device in clean water and they understand the oxygen transfer efficiency. Whereas in process water, because of the constituents of wastewater, you've got your activated sludge, you've got your bugs floating around, even the chemical constituents, the temperature, etc. That all influences the standard aeration efficiency. And what we find is there's a factor called an alpha factor, and I'll just call it like a bucket term for all of the inhibitors that exist to oxygen transfer in wastewater. That's basically what it is.
Mm-hmm.
And our technology is much better at overcoming the alpha impacts within wastewater than fine bubble diffused aeration is. So if you add in alpha as like a coefficient, so let's say call it a percentage. So you multiply alpha by your SAE, and that's your real efficiency in process. We can maintain alpha factors of upwards of 90%, whereas fine bubble diffused aeration is much worse. It's maybe 50 less 40%. And then over time, that performance deteriorates even more. So whereas ours doesn't, because we don't get scaling on, we don't have blowers, we don't have diffuser heads, we don't get scaling on our device. So the efficiency of our device is maintained throughout its lifespan, you know. So I hope that answered the question, but in reality, you could do a 1 hour session on that alone.
I think that's a very good run through it. Fergus, John has asked, is the technology being considered for new wastewater treatment plants rather than retrofits?
Yeah, it's a really good question, actually. Yes is the answer. But what we're finding is the ratio of retrofits to new builds, it like retrofits far outweigh new builds. And the reason why is because of some of the context that we talked about. We can't afford to build new treatment plants in every town and city across the world. So what is predominantly being done is existing treatment plants are being retrofitted to supplement existing capacity or to provide additional capacity. So while we have a number of projects, actually, all of our projects, bar the abattoir example I gave was a new build, because that was actually a new activated sludge treatment stream. All of our other projects to date, I think, have been retrofits, but we will be doing another new build project in Australia, I think next year, with VPA technology as well. So like there is advantages in both new build and existing treatment plant settings, you know.
Yeah, thanks very much. Marcin, just excellent presentation. Thank you. Couple of questions. Wouldn't using vortex system in aeration process affect the integrity of the biomass? And
That's it. Yeah. Sorry, go on.
okay,
Yeah.
yeah, no, we
Yeah.
can take them one at a time. Fergus, that's
Uh,
okay.
Another good question. That's a question that we actually get quite a lot, and for good reason, because like in Marson will know this, but in activated sludge treatment relies on the bugs flocking together. They form flocks, and then you have them in equal distribution throughout the reactor, and that facilitates the treatment. But when you start to chop up those flocks, they're less effective at removing the contaminants in the wastewater. So it's a good question because when you look at our device, you think vortex, high turbulence, this thing is going to shred all of the bacteria to bits. But in reality, we've actually done microbiological examination of flock from some of our installations, and what we don't shear the flock. That's number one. But and I suppose kind of this requires additional insight. But from some of the observation we've made to date, we actually think that we improve flock health to a certain degree. Now, we need to do a little bit more study on this, but we have observed better settlement characteristics at the clarification stage at some of our VPA installation sites. So there's a little bit of evidence, but I'll just caution that by saying that, there's a little bit more research to be done on that for it to be conclusive. But we certainly don't impact the flock. Yeah.
Okay. Second question was, most of the aeration tanks are rectangular. Would that mean that to keep efficiency of treatment requires splitting the tank into smaller units and use of a few vortex units?
Not necessarily. So we have geometrically the vortex powered aeration devices are the same, but that we have scaled up variations. So we have a smaller unit that's the smallest one is 5 kilowatts, for example. The largest one at the moment is 63 kilowatts. So depending on the treatment plant requirements, typically VPA doesn't need redundancy because you can switch the pump out in like 20 minutes. So you don't really need a duty standby machine. But depending on the plant requirements, in most cases, you can just put in a large device. And once you have certainty that the mixing is still going to be sufficient, that's enough. It's not necessary in most cases to put in, an array of smaller devices, but that can be done if there's a particular reason why it's needed.
Okay, thank you. And the last, and I'm not sure whether this is wastewater or the drop shafts. Has energy reuse from the vortex system been considered?
Yeah, it has actually. And whoever asked that question probably familiar with hydropower recovery applications where vortex flows are actually leveraged as well. So it's a really interesting question. In drop structures, it's definitely being looked at currently. I know that for our own technology, it's an area that we are exploring in the background as well. So there is excess energy generated in vortex flow that can actually be recovered at the discharge end. And that's something we're definitely working on. But I mean, on the face of it, our technology, like we've gathered data from these sites, and third parties have gathered data from these sites as well, including looking at energy bills, and we're already saving substantial amounts of energy relative to other technologies. So we're kind of happy with that at the moment, but that's another angle that we've certainly thought of and that we're exploring.
Okay, that's great. And that's all the questions that we have in, Fergus. So again, I'd just like to thank you very much for your time and the pulling together of a fascinating presentation, which covered both, I suppose, a narrative through the technology and provided the technical insight as well. So it's very much appreciated, and thank you very much.